Hello again, Calculus 2. So I'm trying to move into 9-9, geometric power series. There's a lot in there. I kind of focus it down to one or two kind of problems here. 9-9 geometric power series. So now we're looking at a function like this. We want to build a series for this. You know, again, a series could be an infinite polynomial. You could think about building a polynomial. Of course, in 9-7, you learn how to build a polynomial. You take a bunch of derivatives and you find the Taylor polynomial formula. But anyway, I'm going to go straight to a series because these are set up very nice. You know, look at that thing. Doesn't it look like the sum of a geometric series? You know, you worked on this, the formula for the sum of a geometric series when a geometric series has an a first term and an r to the n. You know, this was the sum of the geometric series, and this looks a hell of a lot like that. So maybe my a is a 1, my r is an x, and maybe I could write this as a series. X to the n, my a is a 1, my r is a x. This is x to the n goes from 0 to infinity. So, that was easy. This function can be written as this series, thanks to the connection you make by making it look like the sum of a geometric series. Now, it's a power series. It represents this function. It is this function. It converges to this function. When does it converge to this function? Or for what x values does it converge to this function? Well, back in 9a, we would do a ratio test to find the interval of convergence. But again, if this is a geometric series, we know when a geometric series converges. A geometric series converges when that r, when that absolute value of r is less than 1, or you could say when that r is between -1 and 1. So that's what I want to say. This converges to this function when x is my r, when x is between -1 and 1. And so my interval of convergence is from -1 to 1. Not at the endpoints, only at only between -1 to 1. You know, if you built a little polynomial, plug in a 0, x to the 0 is a 1, x to the first is an x squared, x cubed. So if I took this out, this is the series. I could stop whenever I want to and call it a third, fourth, fifth degree polynomial, type it in my graphing calculator, try to graph this function in a graphing calculator. Just real quick, this function is undefined at 1. So this function has this asymptote at 1. When you plug in a 0, you get 1. So this function, yeah, looks like this. On this side, I think over here it's down here. But you know, so when we say we get this series to match this function, it's only matching it from -1 to 1. That's it. That's where it converges. So if you were graphing a polynomial, a third degree polynomial, for example, you know, it would come up here and it would kind of match it in here. Just from -1 to 1, that's it. You couldn't really get it to match over there. By the way, this is centered at 0. Of course, you can see that it's centered at 0, I guess. Okay, let's do another example. So here's another one. F of x equals 5 over 3 plus 7x. So I want to find a geometric series for this. So of course I made it a little more complicated. But I'm going to get rid of this evidence here. Create a little room for myself here. But I'm still using this idea. So I want to make a geometric power series. Now they tell me I want it to be they tell me it's centered at 0. So I want to get one that's centered at 0. So basically, you know, I don't care what a is, and I don't care what r is. I don't care what a is. I don't care what r is. It's going to have some x's in it. But I need this to be a 1, and I need this to be a minus sign. So what I do is I manipulate this algebraically. You know, to make that a 1, it's pretty easy. You multiply by 1/3. course, that means you have to multiply the numerator by 1/3. That's legal manipulation there. So your numerator just turned into 5/3. Your denominator made that a 1. You distribute across here, and you've got a plus 7/3 x. So cool, we're getting there. I need that to be a 1. You know what? I need that to be a minus sign, and there's a little trick to that. It's easy. 5/3 in the numerator. To make that plus sign a minus sign, you go 1 minus a negative 7/3 x. So there we are. We fit the formula. A over 1 minus r. My A is 5/3. My r is negative 7/3 x. Again, I can write this as a geometric power series. A little more complicated, but not too difficult at all. There's my r to the n. There's my A. We start these at 0 to infinity. And this series is this original function for a certain interval of convergence. If you don't mind, let's find this interval of convergence. Again, it's when the r is let between -1 and 1. You know, if you multiply, you solve this inequality for x, you multiply by -3/7, I guess. That'll put a positive 3/7 here. You'll switch the inequality symbol, because I just multiplied by -3/7. Switch the inequality, that's -3/7. Of course, that just says, I like to read it this way, actually. So, that's what that says. So, that's your interval of convergence. This series is this function. And if I wanted to write out a few terms, I'd have myself a polynomial. This series is this function, but it only converges, it only kind of matches it on that interval from -3/7 to 3/7. Let's try another one while we're at it. Here comes a little more difficult one. But this will be about the end of this little topic here. 11 minus, I made up another one here, 11 minus 2x. But this time, I want to find a geometric power series for this. It looks a lot like this problem, but I'm going to make it different. This time I want to center it at 3. Let's center it at 3. And you know what that means, I hope. You know, this guy's centered at 0. So if it's centered at 3, what I need is I need an x minus 3 in the problem. I'm going to get rid of this, get rid of this. So I have to do more algebraic manipulation, but if it's centered at 3, I'm looking for this quantity. So let's see. I think I'm going to just do that. I'm going to make it an x minus 3. Now wait a minute. What did I just do? I took the x and I made it an x minus 3. You know, if you distribute that -2 there, that would mean I added a 6. Essentially, I added 6. To compensate for that, I'm going to subtract 6. I can add a 6 and subtract a 6. And I've compensated. I've legally manipulated that. Of course, I want to take that 6 and combine it with the 11 here, so that'll turn into a 5. Minus 2, x minus 3. Okay, all right. Remember, I need this to be a 1, so I want to multiply by 1/5. I want to multiply by 1/5. Here we go. The numerator is a 12/5. I just made that a 1. That 1/5 does distribute through there. That's a 2/5, x minus 3. I think we got it. We've got this formula. A over 1 minus r, and A over 1 minus r. I can write this as a geometric series. The A is the 12/5, and the r is this 2/5. Remember, I need the minus sign. Yeah. So the r is not negative. The r is a 2/5 x minus 3. 2/5 parentheses x minus 3, the whole thing to the n. That's my r. N equals 0 to infinity. That was fun. I like it when it's off-centered. You get this extra bit of manipulation you need to do. So we just took this function and made a series out of it. A geometric power series. And this power series converges to this function. This power series is this function, only on a certain interval of convergence. Let's go ahead and find the interval of convergence. It's when this r is, when this r is between 1 and -1. Let's see, what will I do? Multiply by 5 halves. Negative 5 halves is less than x minus 3 is less than 5 halves. I multiplied by 5 halves. Now I'm going to add 3. Add 3 is like adding 6 halves. So that'll be 1 half. That'll be 11 halves. There's my interval of convergence. When x lives in there, it converges to this function. This series converges to this function for all those x's. By the way, what's the center of that interval? What is the center of that interval from 1 half to 5 1/2? The center is, you guessed it, we centered this thing at 3. We centered this at 3. All right, that's 9, 9. Like I said, there's a little more complicated stuff in there, but I keep it pretty simple. So I might be ready to move into 9, 10. Thanks for working hard, and keep learning. Do a little homework.